For the next question, that is question 10. Omega be a bounded smooth domain. 3-dimensional bounded smooth. Open. Anyway, closed. Okay, and closed. I require it to be closed. And the U is continuously differentiable over omega, and X is a vector field on omega, which is C2, twice differentiable. And the nu is the unit normal vector outward, unit outward. On the boundary of omega. Then gradient of U inner product with the rotation, the curl of X equal the surface integral over the boundary, lot of X inner product with the nu. Maybe my X will have a vector notation. Then multiplying U. Here I denote X by X1, X2, X3. I will not use XYZ. Of course, you can also use the XYZ, okay, to denote the component of point or vectors in 3-dimensional space. So how to prove this? To prove this result, we first observe the quantity in our problem. Let's have a look on this. This is just U lot X inner product with nu. Okay, so this is a surface integral over a closed surface over the boundary of a domain. The integrand is a vector valued function inner product with the outward normal vector. Therefore, we need to apply the divergence theorem, of course, because this is a vector field inner product with the outward normal vector. So the natural idea is to apply the divergence theorem. So the idea is apply divergence theorem to this vector field. The lot X is a new vector field generalized from the old one, X. So this is a vector field. Vector field multiplying a function is still a vector field. So this new vector field we denoted by capital F. So we want to apply the divergence theorem to this capital F. We obtained that is F. Of course, this will be the divergence of F. Okay, so we need to compute the divergence of F. The divergence of F is a multiplication of the scalar function U with the vector function lot X. So by the proposition, by our previous proposition, we mentioned several times already. this proposition. The divergence of a scalar function multiplying a vector field equals the gradient of the scalar function inner product with the vector field plus the scalar function multiplying the divergence of the vector field. Using this result, we have we should have this will equal the gradient of u inner product of the root x plus u multiplying the divergence of root x. Okay, but I will tell you that this is 0. Given a vector field, taking the root, that is the curl of the vector field, you obtain a new vector field. A general result is that for such a vector field, the divergence is 0. So this is exactly the gradient of u root x. So this is substituting the computation of divergence f here into this computation, we obtain the desired result and concluding the proof. So it suffices to verify that the divergence of the root x is 0. Okay, let's do this computation. So the computation is straightforward. This is the divergence of root x. Root x is the determinant of, maybe I will use the bar. This is the coordinate unit vector, then partial with respect to x1, this is the x2, x3, then the component of x1, x2, x3. Okay, so this is the divergence of this vector field. The first component is this determinant of this. So this is d2x3 minus d3x2. Then the second component is you erase this and this, then x1 d1, x3 d3. So that is d3x1. d3x1 minus d1x3. And then finally you erase this and consider this determinant. Okay, so this is d1x2 minus d2x1. d1x2 minus d2x1. This is the root x. Using the determinant notation, it is easy to remember the definition of root x, the curl of x. But you need to expand the determinant with respect to the first row to obtain the exact expression of all the components. That is given by the linear combination of the partial derivative of the component of x as shown here. Okay. Now, to continue this computation, we apply the definition of divergence. That is, the first component taking derivative which x1, the second component taking derivative which x2, the third component taking derivative which x3. The sum will give you the divergence. Therefore, this is the d1, d2x3 minus d3x2 plus d2, d3x1 minus d1x3 plus d3, d1x2 minus d2x1. Then you expand this, you will obtain some linear combination of second order derivative. You will see that this term is d1 d2 x3, and we also have this term. This also gives us d2 d1 x3, but with a minus sign, because x is C2. X is a C2 vector field, so the components are the second derivative of the components are all continuous. Therefore, d1 d2 can be switched. So this is equal d1 d2 x3. Therefore, this term cancel with this term. Similarly, the other term, for example, this x2 term, d1 d3 term can also be cancelled with this term. d1 d3 x2, d3 d1 x2. This is negative sign here, but this is positive sign, so cancel. So you also cancel these two terms. Okay. Finally, for x1, d2 d3 x1 and d3 d2 x1 also cancel. So in conclusion, the result is 0. So this proved this identity. This proves that taking load and then divergent result is 0. This is what we need in the proof of this question. So we have this, and we have already proved this. Okay.